Hello everybody, I'm Markus Hauck from Concentric and I welcome you to my talk about how to free all the things. I know the first talk after lunch is always the hardest, so I'm really happy that you're here. Okay, so when we talk about free things, the best known concepts are probably the free monads. They are currently around everywhere. A little less known are free applicatives, but there are actually also other structures like free monoids, or actually you can put free in front of a lot of stuff. So the goal of this talk is to explain the technique what makes free x a free x. And I will show you the technique, how to do it. It's pretty mechanical. And then we will apply the technique to different examples. So yes, we will also do monads. I hope for you that the takeaway will be that it's actually easier than you thought. And maybe you will also afterwards find stuff that you can free. If you want to, the source code is on GitHub. This link will also be on one of the later slides again. Okay, so let's get started. So if you look for the definition of what a free functor is, well, a free functor is left adjoint to a forgetful functor. Easy, right? So we already got our meme there. To put it a little bit in more words, well, a free thing, let's call it free A, on a type class, A is itself the A, and a function that we call inject in here, sometimes it's also called lift, that receives an x of type A and returns us a free A. But there are some rules, so it has to satisfy that for any other thing, let's call it B, and a function, let's call it f, that goes from A to B, there has to be a unique homomorphism, so this strange word again, we call it G, such that G composed with inject is f. So what this in essence means is that there's no added structure when you have your free and afterwards you interpret it. Okay, this still sounds pretty complicated. I promise you that it's easier than you thought. So the good thing is, or the good news is, that there is an easy mechanical recipe on how to free your things. And this is you first define the AST for the operations of your type class. Then you add an inject clause in there. We will see that. Then you write your interpreter, and then you have to check the laws in the last step. But before we go into the first example, why should we free anything at all? The point is that you get a nice API based on the operations of the type class. So for monads, it's something that you can flat map and map over, and you can use it in for comprehensions or in do notation. And this is an API that most of the users are pretty familiar with. So this is an added bonus for your DSL. And you can also use a free x as if it was just a x. So you can use a free monad as a monad, you can use a free applicative as an applicative, and so on and so forth. And what you get is you have the actual program reified into a data structure. And you can take that data structure, analyze it, optimize it, and then interpret it into the actual program. So you can have one program, but many interpretations. For example, you can analyze the execution. You can have multiple interpreters running the same program and get different results. Small disclaimer before we go into the first example, I will mostly be talking about deep embeddings or initial encodings or also the data structure representation. There is another approach that is called finally tactless, which I'm not going into here, and I will also not go into too many details on how to optimize our free structure. Okay, with that aside, let's first free the monad. And for that, we first look at the monad type class. So we have the operation that is called pure, which takes an x and just lifts it into the type constructor. And we have the operation called flat map, which given a value of type fa, that is an a wrapped into the type constructor, and a function from a to an fb, gives us back an fb. So you should all probably know the flat map operation by now. And the monad type class comes with some laws. So there is left identity, which says that when you apply pure to a value and flat map over it, it should be the same thing as just applying the f function to the a. And the same is on the right. So if you have a value of fa that is already wrapped, and you flat map over it and just apply pure, that should do nothing. And there's also this associativity law, which is actually hard to see in the normal case. If you have a wrap value of type fa and you flat map over it and then flat map again, this should be the same thing as flat mapping and doing an inner flat map in this one. We will come back to that in a moment. Okay, so we have this type class monad, and now let's just apply our recipe. So the first step is we define an AST. Okay, that's pretty easy. We can use a sealed abstract class. We call it free. We could also have called it freed monad. And then we have one case class for the pure case, which, surprise, has a value of type A, and it extends a free of f and a. Then we have another case class called flatmap, which, surprise again, is just the same as the operations in the type class, takes a wrap value of type fa of type free of fa, and the function that is the actual bind. And then if you go back to the recipe, the next step is to add this inject clause. So the third case class is a special node named inject, which, given a wrap value of type fa, so it's not yet a free, extends the free of f and a. And with that in place, we can actually already define the monad instance for our data structure. And whenever we call pure on with our free monad, we just wrap it into a pure node. And whenever we call flatmap, we just wrap it into a flatmap node. So essentially what this does when users use our free monad instance, it just builds up these nodes. And of course, we also have to write an interpreter. So we call it here runFree, and it's given the natural transformation from the f-type to some monad. So this is what we say here. This is the target monad. This is our actual function that will do the interpretation. And then we just pattern match on our instructions. If it's a pure node, we can simply call the pure from the monad we have, from the target monad. If it's a flat map, we just call the flat map and run free recursively down our AST. And if it's the inject case, we just apply our actual function that we get in, then translates into the target monad. So this is the basic structure of our interpreter. But if you recall, the free monad has some, or any monad has to satisfy some laws. And we spoke about the associativity law, for example. So if we have this flat map followed by a flat map versus this nested flat map, it should actually be the same. But if we look at our case, if we use our free monad instance, in the first case, we will get a nested flat map node. And in the other case, we would get a flat map node, and inside in there, we have a function that will produce another flat map node. So those two are not equal. That's easy to see. So that's obviously a violation of the monad laws. So what about that? If you want to be a free structure, you have to satisfy them. So if you are a programmer, you might reason that, well, who cares? After interpretation, we will no longer be able to see it as long as the target monad satisfies all of the laws. But the mathematicians will tell you, no, then it's not a free structure. So there's actually kind of a trade-off that you can place there. And the trade-off is you can either satisfy all the laws during construction, or you can make some trade-offs for performance and only do them during interpretation. So let's get back to our free monad. So one common transformation, at least in Scala, is to associate all of the flat maps to the right, because this avoids having to rebuild the tree repeatedly. And how are we doing this? Well, we can do it during construction time. So in theory, it's still possible to construct invalid trees, but we hide it by changing our free monad instance. So users should never be able to construct the tree by hand. And for this, we changed the pure case. If you recall, we need to satisfy the left identity. So when we call flatmap on something that is pure, we pattern match on it, and we just apply the f of x directly. So we have satisfied the left identity law. If the node is a flatmap node, we can pattern match on that one again, and we can reassociate everything to the right. And if you think about why this reassociating in Scala is good, then in this case, we always will get a flatmap node with something in there, and then a function. So whenever you run this, you first can pattern match, execute the first instruction, call the function for the rest. So that means no stack problems. So this is actually the trick how we handle stack safety in Scala for free monads. And you can ensure this with the associativity law. Okay, so what do we get when we free monads? Well, we have the DSL with automatic expressiveness. All of our users are pretty familiar with it, and we can do with the programs whatever we want. And the monads gets you context sensitivity, you get branching loops, basically any fancy control flow that you can imagine. The big drawback, however, is that the interpreter will have limited possibilities because you cannot really inspect the functions inside the flatmap nodes. But that's something you have to live with if you are using free monads. Okay, so we freed monads. Let's go to applicatives and apply our recipe again. The disadvantage, as I said, of free monads is that we can't analyze our programs. So with free applicatives, we can be able to do this. So let's try free applicatives. And our recipe is the same. So we define our AST, add the inject clause, write our interpreter, and then we check the logs. Okay, so the applicative type class is shown here again. I again included the pure node, the pure method, and we also have this method called app, which given a function that is already wrapped in some higher kind of type constructor, and the value that it can be applied to just applies the function and gives the value back. Okay, so we define our AST. We have the pure node again. We have a node called app, which takes the arguments of the method, and we have the inject node. And there are some laws. So the problem here is that, for example, in the identity case, in order to satisfy them, we would have to somehow check whether this app of pure contains the identity function. And good luck with that, because we cannot easily compare functions with pattern matching. And the same for the composition law. So this is also not too interesting for us, because you cannot easily enforce that, because we would have to make sure that we know that this is the compose function. So we can't really do anything here. But the last two look more interesting. And there's the homomorphism law, which says whenever you have an app node that just contains two pure nodes, then you can just do a pure of the function applied to the value. And then there's interchange law, which says that you can swap around the app and the pure node in some cases. Okay, so when we now create our applicative instance, we can again do the optimization in order to satisfy the laws. So we can pattern match on our FA, B, and our FA. And if it's two pure nodes, well, that's just a homomorphism law, so we just directly translate this into the more efficient pure of Fx. And if it's the pure on the right-hand side, then we can just apply the interchange law and optimize our data structure in this way. Okay, so we satisfy the laws, at least the last two. So this is where I said it's a trade-off, because it's more like an gradient, where you can satisfy most of the laws, but not all of them. But after interpretation, normally if the target is lawful, you won't have any problems. And then we can just write our interpreter that pattern matches on our node. If it's a pure of x, we just delegate to the applicative instance we are interpreting into. If it's an inject, we just use a natural transformation. And if it's an app node, we just recurse down our nodes. And that's basically it. So we already freed our applicatives. That was very similar to the free monad case. And we get back in BSL with applicative expressiveness. So we can no longer depend on previous effectful values, so the computation is more or less fixed. But users are still familiar with the applicatives, and then they can use your DSL. And you also get a lot more freedom during interpretation, and you can actually do a lot of stuff in there. You can, for example, execute your applicative in parallel if you want to, without the user even knowing. Okay, so we freed our applicative. So let's take the next structure. Let's go to functors. And we basically apply the same recipe again. So we start with a type class called Functor, which has the map function that, just given the value that is wrapped in an FA and a function from A to B, applies that function. So this should be pretty boring by now. We have our new astute abstract class free functor. We have a case for fmap, and we have a case for inject. But now if you look a little bit more into the inject node, you will see that it's not really that interesting in this case. And we can actually get rid of this by just making it a method called inject, and then using the fmap node and apply identity in here. So we can get rid of that extra node in our AST. And if you look a little bit more into this code snippet, you will actually see a code smell that any OOP programmer will tell you there's a code smell. Does anybody see here? Exactly. So we have an abstract class and we have only one subclass. So where's the sense in that? So why don't we get rid of this? And if you look at this, why do we have this subclass? Well, our free functor has 2 type parameters and our fmap has 3. So we somehow need to hide that extra type parameter in order to get rid of the class. And we can do this by making it existential and using a type member in Scala. And then we can just say the fmap node has this existential type x, and everything will work out, and we can just use it also in the inject method. So we have minimized our structure even more. Okay, and now if we want to be really cool, we just rename it to coioneda because that's what we're actually doing, and then every category theory mathematician will be happy. Okay, so then we have to create our free functor instance. And in the case for the map function, we just create the new coioneda node, and we have to assign the x type, the type member, to make everything work out. And then we have just function composition, because we take the function that we already have in here and then just compose it with a new function when we map over it. That means if you start with an fmap of identity and then you map over it, you just start composing functions into your node. And then the interpreter is pretty boring because you just get in your node and then you call the fmap of the actual functor over it and apply it. Okay, that's actually pretty boring because your DSL will only consist of maps. So the only thing that users can do is they can call map and map again and map again and so on and so forth. But this is actually still interesting because you get map fusion for free. So whenever your users are using the DSL, every map will be fused. So if you only have a functorial DSL, that's still not very interesting. But you can, for example, nest this free functor into a free monad. And then you have a free monad that performs map fusion. That's pretty cool. But the interpreter, as I said, is pretty boring. But it was still fun, and we could just apply our recipe. OK, so what about monoids? Monoids definitely want to be freed as well. So we have our simple type class monoid that has the def empty and the def combine. And empty just summons a value from nothing, and combine combines 2 values into 1. OK, so again, we start with our normal pattern. We have our 3 cases. One is just the empty case for the empty function. One is the combine case for the combine method. And we have our inject. Not surprising. And again, we have some laws in here. We have left identity, which says that if we combine the empty and the x, so this plus this pipe plus pipe is actually the combine function in infix here, you will get back the x. And if you combine x with empty, you will also get back x, and it has also to be associative. So that means it doesn't matter where you group the parents. OK, so let's try to instead enforce those laws in our structure directly. So instead of applying them when we call our instance functions, we want to bake them into our structure. And our goal is to have our structure being correct at all times. So even if users want to construct them on their own, they have to satisfy the laws. And we have to make one arbitrary decision here. We have to decide whether we want to associate to the left or to the right. And I decided for the right, and you will see why in a moment. OK, so we have our AST. And now we just have to make sure that we cannot combine in some cases. So when you look at the combine node in here, we want to be the left-hand side to be not combine, and the right-hand side can be anything. So for this, we add a new trait that we call not combine. And we take the empty node and the inject node with not combine, because they are obviously not combined. So by this, we just exclude combine nodes on the left-hand side here. OK, that means we can already guarantee associativity because everything will be associated to the right, because combines always have to be on the right-hand side. OK, so we still have to take care of the identity laws. And so we have to take care of the problem with the neutral element. And the question is, can we get rid completely of the neutral element? Well, no, we can't, because there are still expressions like, for example, only the empty case where we have to carry this around. So instead, we can limit ourselves to have only a single empty element in our structure. And the idea is, again, to restrict our combine to have only real values on the left-hand side. So previously, we had inject and empty on the left-hand side. Now we only want real values in there. OK, so we have our case class inject that only takes some value of type A. And in the combine case, instead of having this trait with a not combine, we only have the inject case. So we don't allow the empty case anymore in there. But actually, we can completely get rid of the inject, because if you look at this snippet, then the inject case is just a new type wrapper around the A. So let's get rid of that one. So we still have two cases remaining. The empty case, which we have to carry around, and the combine, which only allows real values on the left-hand side, and then more combine on empty nodes on the right-hand side. This might start to sound familiar to you. And we can write the monoid instance, and the empty case just returns the empty data structure. And the combine, well, we have to do a little bit more in there, because we have to reassociate everything to the right if necessary. So in the combine, we match on the x here. And if it's an empty, we're OK. If it's in combine, we have to wrap everything into another combine if it's already here and combine in here. So we associate everything to the right and recurse down. OK, so let's just rename our constructors. Let's rename our free monoid to list, our empty to null, and our combine to const. And now we have lists. So actually, now you can see why lists are the free monoid. And we derived it ourselves. OK, so we freed monoids. So you get back a DSL for combining things. And they work beautifully with folds. So you can get a lot of structure for your DSL without doing a lot. And the interpretation of your monoid can actually be in parallel, because if you have this tree structure, you can actually, because of associativity, evaluate them in parallel and then combine them in any order. OK, so this seems to work out pretty well, our recipe. And now that we can free almost anything, what should we free? And up until now, they were like very common structures, but let's look at something that is more interesting. And I think it was several years ago when I read a blog post by Chris Duccio about free objects, and he was freeing a Boolean algebra. OK, so our recipe is the same. We define our AST, we add our inject node, we write our interpreter, and we check the laws. So Boolean algebras are a little bit different than what you normally know. You have the true case, you have the false case, you have not that just represents negation, and you have the and the nor operations. So it's kind of like two monoids fused into one with negation as an addition. OK, so let's define our AST. We have our student object class free bool, and we have our case objects for the true case. We have a case object for the false case. We have the case class for not, we have a case class for and, we have a case class for or, and we have our inject case. So it's the same pattern as before. And then, of course, we need to somehow interpret our free Boolean algebra. And for this, we again take a free Boolean algebra, or a not free Boolean algebra as our target interpretation. And then we just pattern match on our instructions. If it's true, we just return from the target algebra the true. The same for false. If it's inject, we just apply the function. In the not case, we call the negation from the target Boolean algebra, and we recurse down with our interpreter. And the same for the or and the and case. OK, so we have freed bool. That was simple. But what can we actually do with our discovered structure? And there's a quick reminder, so you can use basically any Boolean operators, whether they are derived or not. So you can use true, false, and, or. You can also use the XOR, implies, NAND, whatever you can derive from those basic operations. And here's an example where we apply this whole thing. So we have a sealed trait that is called search. And then we have different cases, like we have something that matches on terms and takes a string. We have an after constructor that checks whether something is after some date. Something whether it checks whether the term t occurs in the text or whether it occurs in the URL. So those are the different cases of our DSL. And then you can define the usual smart constructors that will have the lowercase names of the constructors and just wrap everything into our free Boolean algebra. And after sneaking in some syntactic sugar behind the scenes to get infix operations, you can write programs like this. So you have some search predicate that checks whether FP occurs in our terms, whether it's after the 1st of 2018, and it also makes sure that there's not Java or Spring in the text and in the terms, and the URL should have LambdaConf in it. So this is we used our DSL to construct a basic predicate on something. We have not yet defined on what. And for that we can define, for example, so this is just for the sake of the example, a simple site representation. So this might sit in some database or whatever. And it has a list of terms, the URL when we index that site, and the full text. And all of our predicates will be run against this data structure. Okay, so we need to evaluate our search predicates. So we need our interpreter. And we get in a predicate of type free bool over search. So search is our language. And the site we want to check against, and we return a Boolean. And then we just pattern match on all of our different language instructions. If we check for terms, we look into the terms of the site and check whether it contains the T. For the after, we check whether the indexed at date is after the date that is in the language. The same for the text and the URL. And then we just call our normal free Boolean algebra interpreter with our predicate and our net. So the net is the natural transformation that performs just the interpretation of our language, the search language. And then, for example, we can, for example, look at all sites and filter them with our evil search predicate, and we would get back all sites that satisfy the predicate that it has the term FP is after the 1st of 2018 and contains in our LambdaConf and not Java or Spring. So we actually can model a lot of our complex logic into the simple Boolean algebra structure. Okay, but actually there's a lot more that we can do here. For example, we could do short-circuiting or optimization of our program. And we can also care about predicates that don't have all of the information available yet. So, for example, we can have a predicate that checks whether the full text contains something, but what if we loaded just the metadata of a site and not yet the full text? So the idea is that you partially evaluate your predicate, and if you can short-circuit it, then you can just avoid loading the text from the database. And you can also have a core language versus an extension that where the core language is a set of primitives, and you can just build on top of this and derive more instructions. And Chris also demonstrated this in the blog post that I will link again at the end. And the idea is just to translate the rich language back into your simple search language, and then you can use your existing interpreter. And you get all of the advantages that you don't have to provide any more infrastructure. You just translate this rich language into your core language, and you can reuse all of the rest. So you can optimize your Boolean algebras. I'm not sure whether I got all of the optimizations that are possible, but you can, for example, make sure that double negation is removed. You can make sure that OR of true and something is short-circuited to true, and the other way around. And you can also make sure that AND of false and something is just short-circuited to false. So if you use this optimizer before the interpreter, you can avoid unnecessary evaluations. But let's get back to the partial evaluation thing. So the idea is, as I said, you just have the metadata of the site and the text is maybe still in the database. So you want to avoid to load this whole full text of the site if you can avoid it. And we just evaluate as much as possible without knowing the text. And it would be optimal if we can reduce everything to true or false without ever touching the text. And if not, we can still send it on to some other system that is able to load the text from the database. And given that we don't have any functions in our AST, we can just serialize it to JSON or protobuf or whatever. Something that we cannot do with free monads or free applicatives, because they might have functions, then it gets a lot uglier. Okay, so here's our partial evaluator. It just takes in a free Boolean program, and then this f function that goes from this a to an option of b. So that means in some cases we might get back a none, and this means we can't evaluate this because we only do partial evaluation. And again, we pattern match on our program. If it's a true, well, we then just return the right of b.true, which is our target Boolean algebra. In most cases, it will be just your normal Boolean. And for the OR case, for example, here I did not show all of the cases. We run our partial evaluator for both branches of the OR, and then we check whether it's fully evaluated or not. And if it's fully evaluated, maybe we can perform short-circuiting with our optimizer. Okay, so let's apply this to the site metadata. Let's say you have this case class site metadata that has all the terms that your normal site has, but it's lacking the full text. And then you can define the partially function that takes the site metadata and your normal search predicate, and it checks whether it can check the term, the after, and the in URL case, and for the in-text case, it's just none. And if you apply this to our original predicate, in some cases it might be able to evaluate to true, and in some cases you might still have to load the text. But in all of the cases where you can evaluate it to false or true, for example, if FP is not on the term list, or when it's not after, when it's before 2018, you will always be able to evaluate it to true or false beforehand. So this is really powerful because you can avoid unnecessary evaluations in there. Okay, so we freed our Boolean algebras, and I think this is a good example of an underused free structure. And you can just discover those by applying this recipe. And we can even have partial evaluation on this, so there are also other structures where you can do similar tricks. And the cool thing also is that given that it's not as powerful as a free applicative or free monad, so it doesn't contain any functions, we can easily serialize it to JSON, protobuf, or whatever. And you can, for example, also think of use case where you evaluate some of those predicates on the server side, and otherwise you serialize it to JSON and send the rest back to the client. And he will only have the remaining predicate to evaluate. And yeah, the AST of the free Boolean algebra is not really minimized. You might have seen that. And there are also some laws that are not satisfied in our construction. So if you want to, you can try to minimize the AST like we did for the free monoid. But spoiler, it's not as easy because there are a lot of laws in there for Boolean algebras. Okay, so here are the resources that I used in preparing this talk. So there's the blog post from Chris Ducchio, and there's also the link to my GitHub repository. So with that, I hope you know how to free things, and let's go out and free some more things. Thanks.